Imagine a calm, spacious house. Inside, 5 roommates are relaxing, completely at peace with one another. Nobody is fighting for space, and everything is quiet. But suddenly, a crowd of uninvited guests marches right up the walkway, rushing the doors and crowding the windows. In chemistry, that house is a central metal atom, and those 5 roommates are its 5 distinct living spaces, which we call d orbitals. Normally, when the atom is left completely alone, all 5 of these d orbitals sit at the exact same energy level. Everyone is equally comfortable. Those uninvited guests crowding the outside of the house are molecules called ligands, and they bring a problem with them. They carry a negative electrical charge, the exact same charge as the electrons already living inside the atom. Because negative charges repel each other, the arrival of the ligands creates a violent pushing match. The electrons inside are repelled by the electrons outside, causing the overall stress inside the atom to skyrocket. The atom can't just ignore this pressure. To keep from falling apart under all this crowding, it has to completely rearrange how its internal energy is distributed. The incoming ligands don't just surround the atom in a random circle. They approach along very specific paths, marching straight down the main axes. Think of these as the central hallways of the house. Meanwhile, the diagonal corner rooms are mostly left alone. This animated diagram shows exactly how the atom reacts. 2 of the living spaces sit directly in those main hallways. They take a direct hit from the incoming ligands, causing their stress, or energy level, to shoot way up. But the other 3 orbitals are tucked away safely in the corners. Because they avoid the direct traffic, they actually relax, and their energy level drops below where it started. This physical division of energy levels is known in chemistry as crystal field splitting. To keep track of who is where, we give these groups specific names. The 2 high-stress direct path orbitals at the top are labeled as Eg, and the 3 lower, tucked-away orbitals at the bottom are labeled as T2G. We can measure how much stress this split relieves. This energy gap is represented by the symbol delta. You can think of it as the price the atom pays to stay stable while being surrounded. The atom uses this structural divide as a logical shield, shifting its energy around to survive the intense magnetic crowding. Which brings up an interesting question. If you change the total number of invading guests, does that change how drastic the energy split gets? This chart compares 2 different scenarios to answer that. On the left, we have what's called an octahedral setup. This happens when exactly 6 ligands attack the central atom from all sides. 6 invaders create massive repulsion, forcing a massive energy gap between the upper and lower levels. On the right side of the chart, we have a tetrahedral setup. In this case, only 4 ligands approach the atom. Because there are fewer invaders, there are fewer direct hits on the atom's living spaces. That means significantly less overall repulsion, leaving us with a much smaller energy gap. Since 4 guests create less friction than 6, and because they avoid those central hallways entirely, the total pressure drops by more than half. It lands at a very specific fraction. The stress in this smaller group is exactly 4/9 of the larger gap. Coordination chemistry focuses on these precise arrangements, mapping out exactly how atoms stay stable when their personal space is invaded. So if you were stuck in a crowded house party, which roommate would you be? The Eg taking the direct hit in the hallway, or the T2G hiding quietly in the corner? Let us know in the comments.